Good evening, everybody. Day 4 of our CS47 class. We have some participants, 21. That's good. All right, let's get started. Remember, this is being recorded and this is also live in the YouTube. So we were supposed to be reviewing the number system, lecture 3, as far as I remember. Anyone has any question on the topic? Let me also go and review if there is any question on the discussion side. No, I don't see any. Okay, let me do one thing tonight. Let us go back and do some more review on the lecture 2 because that is very fundamental and very important to understand the computer system concept hardware wise, okay, how this component works and interact with each other. Uh, Remember, like towards that lecture 2's towards the last is a control system model where we talked about this 5-stage execution: instruction fetch, instruction decode, execute, memory, and write back. And somewhat in the same line, we discussed that in the day 1. Remember that that discussion we did with respect to thinking that memory, controller, ALU, all of them as an actor, and they are taking some action to execute a high-level program C equal to B plus A. Let's review in terms of that high-level program, but in somewhat details. Details in the sense, remember the second day's lecture, second day's discussion we had, there we try to see the interaction between the processor and the memory as a real digital signals, and how these signals are uh, changing its logic values for different operation, read and write, and how the timing diagrams are written, drawn down at each timing step. So we'll somewhat use similar kind of schematic diagram to represent the digital system instead of actor and action style representation as we did in the day 1. So we'll represent as a day 2 that type of schematic diagram, and we'll pick up the same example as we did in the day 1, the very simple program C equal to A plus B, and see how in the real system this whole thing is executed in a five-stage action cycle, like instruction fetch, instruction decode, execution, memory, and the write back cycle. All right. So to do that, first let me share my screen. All right, and then start this one. I hope it is coming up for everybody, and let me just preview a little bit on how it is being recorded. Okay, all right. Maybe I'll turn off my video after some time. Anyway, so here we are presenting the whole system as a logical connection. We are representing the electrical connection as a logical connection with these 3 components or 4 components we have. We have memory, which needs address, data, read, write, and definitely everyone needs a clock. And we have register file, which has 2 address port in it, address 1, address 2 for reading. And for data reading out, we have 2 more data bus, data 1, data 2. And then we have separate write address and write data bus connection for the register file. Unlike the memory, memory has only one single bidirectional data line where either controller sends the data to the memory or memory sends the data back to the controller. But between the register file and controller, being register file is a very special type of memory. It has separate data line for writing and reading. And on top of that, we can read simultaneously two data together from this piece of memory, which we call register file. So that connection is made, the read-write control connection is made, and on the ALU side, we have two operands, one operation code, and the results will be from ALU towards the controller. And controller side, we have marked those logic signal values which are being connected to the other side of the different components. And also note that this clock, I have shown it separately, but they're really coming from one single clock, and they're just being from a clock device, they're being connected to all this clock pin it has. I just omitted that to just keep the diagram simple. Any questions so far, this point?
Professor?
Yes, Rahul.
Yes, I had a question. So I had posted this in the discussion also, but I didn't get a response. It was a question on register files and how they work. So in register file, you can yeah, you have a separate data line for write and a separate data line for read. So you can do a write operation followed by, I mean, a read operation immediately followed by a write operation. And an example was given in your lectures. I want to know what would happen if you give a read operation immediately followed by a write operation on the same address.
Okay,
How would the mechanism
I
work
answered
out?
that in the discussion, but anyway, I think I saw your question. I answered to that, but let me also say, so this happened like the previous data store that will come into the data line,
Okay.
and the new data will be replaced. So it is not that the new data will start appearing on this data. So internal circuit structure is such a way that with that kind of operation, your previous data only will go out as a data read, when it is being written with the new data.
I see. Okay. Thank you.
Yeah, so basically when you go into CS47, we'll build up this register file from a logic gate, and there you will see how this magic happens. But this is the internal logic and electronic structure. Okay, so behavior wise, it's like this. All right, now let's also, on top of this, let's put the direction. Okay, so this arrow means the information flows from which side to what side. So most of the cases it is obvious which side to what side, except for the connection between data line in the memory and controller, because it varies time to time. One time data flows from controller to the memory in case of write operation on the memory, and in case of read operation from the memory, data flows from memory towards the controller. So that's why there is no arrow sign for that specific pass. But other than that, everything is kind of given a direction. So obviously you can say that what are the input buses or input signal for a given component. Anything coming towards it is the input bus or input signal, and anything going outwards from it is the output signal or output bus or output logic. All right, now so now that we are clear on this diagram, on this schematic diagram, let's move on to this simple program, right? So we started with this simple program, high level program, A = 10, B = 20, C = A + B. And Then we also assume that these high-level variables are assigned with certain memory address by the compiler, which, for example, in this example, we assume that compiler assigned address 0, address 1, and address 2 for this corresponding variable A, B, and C. That's number one. Number two is that compiler now broke down this high-level program, okay, into smaller basic steps, like 8 different basic steps, right? 1, 2, 3, 4, 5, 6, 7, 8. 8 different steps. And let me explain here what these steps really means, or at least the notation. So whenever you see a R follows with some indices, this is kind of array like notation. You are familiar in the high level programming. So I have used that notation. This really mean is that you are accessing the register file location 1, okay, or index 1, whatever way you want to think. And this is, for example, if you see a R3, this really means you are accessing the value at the location 3 of register file. So accessing this value, whatever that store is. So this is more like notation wise meaning. So similarly, we have accessing data accessing notation for the memory, which starts with M, and its index or script subscript is becoming like this. This become a function. This really means, this means I want to access an address from an address which is sum of the content of R0. So whatever 0 content is plus 0 on top of that. So basically, if you see in this system, 0 is 0. I'll come to that in a minute in a little bit of this special register. But 0, R0 value is 0. So I am really accessing the memory 0 plus 0 equal to 0. The memory address 0 I want to access here. Similarly, for example, here it means access the value in the R0, add on 2 on top of that. So my result becomes 0 plus 2 equal to 2, and access that memory location. So it's essentially accessing 2. Any question on this notation? Okay. So now we are familiar
Not on
with,
the notation.
yes.
Wait. What is the reason you gave for putting 0 as the 0 index of register file?
Yeah, I'm coming to that.
Okay.
Just hold on.
Cool.
Okay. Now let's look at the steps. What this really means is that you pick up the value in the register 0, add 10, and store that addition result into register 1. And this sentence really means you compute the memory address, whatever that address comes out, you write into that location the content of register 1. So you basically read from the register 1 and write it into the memory, that corresponding address, whatever you are deriving from this expression R0 plus 0. And then similarly, it is R1 equal to R0 plus 20, really means you access the value from R0, add 20 on top of that, store it in the R1, and so on and so forth. Then the other one is R2 equals memory something, means you are really reading from a memory address and storing back that value into the register. So this is the programmatic conception here, what I'm trying to present you. And you will see later, each of them actually can be written in terms of assembly language format, each of them. Okay, so far let's just keep it as a conception level. Now let us come to this part, why it is a 0. So for computing system, especially for the system that we are going to study, which is MIPS processor, MIPS processor, it has a constant register which is called a register 0, and which is index is 0, and it always contains the value 0, and no instruction can override this value. So in other sense, this register for this system is a constant register. You cannot override it. Okay, Rahul, is that like clear your concept why I put 0 there?
Yes, that clears it. Thank you.
Okay. All right. Now we know, we have seen that previously, after compile your high level program into some sort of lower level of program, then assembler tool comes in picture and convert this instruction into the machine code. And then this machine code is going to be executed. So when we start executing a program, these machine codes are loaded into part of the memory. And let's say we store it from, load it from 3. It is not that simple in the real world, but let's just simplify our life and assume that this all set of machine code is loaded from address 3 in the memory. So we want to start executing. So two things happens here. One is, remember that program counter that we discussed in the very first lecture. So that value is changed to 3, and your program is loaded into the memory from the address 3, and then controllers start executing this program. Okay, this exactly what happens when you start executing any program in your system. These machine codes get copied over the memory, program counter gets updated, and controllers start executing your program. Now, when it start executing, it's basically first go into your very first state. It's a state machine. And this very first state is instruction fetch, that in the clock cycle number 1, your clock signal goes high. So the green is high, red is low. So clock signal goes high. Your register file, look at the read-write signal. So these are the main signal that you need to control, because this controls the behavior of the register file. And definitely what you don't want to do is to write anything unwanted into the register file. So it is very important that we keep, or controller keeps these two control signal at bay, so that nothing happens inside the register file in terms of its content. You don't want to accidentally change the content of the register file. And that's why it is given in the no operation situation, read 0, write 0. So nothing is going to happen. Where for the memory side, it is trying to do a read to 1, write to 0, and it sends that address 3. So it is coming from the PC to the memory. And other signals I kept it black, because now that logic is really don't care. It doesn't matter what logic is that. So I just kept it black in that sense. Now next, what happens? Clock goes low. As you remember from the last lecture, at the lower clock cycle, lower logic, like nothing interesting happens. It's just there. So it goes low. Now next, clock cycle 2. Clock goes high again. Controller goes from instruction fetch to instruction decode and register fetch. So at this point, memory returns the data from address 3, right? It returns the data, and controller put the memory in the no operation mode, nothing read, nothing write onto that point, and also parse and understand this machine code. And here it understands that, hey, I need to read from register 0. I need to retrieve the content. So at the same cycle, it puts the register file into read mode. Look at this, read equal to 1, write equal to 0. And it sends that 0 address, it parsed out from this machine code, 0 address to the register file. Now, since there are two address port, it just sent out to both of them as 0. Okay, so nothing big deal about that. But it tries to read only one. One address would be sufficient, but since there are provision for two of the address, it just sent same content to both of the address. It tries to read from address 0. Then next, clock goes low, nothing happens. Clock cycle 3, now it comes from instruction decode stage to the execution state. Here, at this point, register file returns back that content, result of that previous read, which is read from register 0, which is 0. So it gives out this 0 towards the controller. And controller at this point knows that, hey, whatever registered file returns back, I need to add 10 on top of that. So what it does, it deploys the ALU, it requests the ALU, it sends the operands 0 and 10 over it, and with some operation code with represent plus. By the way, there is no character, as I said, in the computer world. Everything is a number. Just for the simplicity, I just put a plus sign there. There is some code, like some value on the 5-bit value on the operation that represent addition. But anyway, that's not important. Important is that controller requests an addition operation to the ALU at this stage. Clock goes low, nothing happens. Now next cycle, controller goes into mem state. ALU returns the result of that addition, which result is 10. Now at this point, this state is involved only with the memory access of the data part. Now the question becomes, is this instruction involved in data memory access in any way? It's no, it's basically register bound operation. I'm reading from one register, adding something, want to send back that into another register, that result. So that's why nothing happens in this state. It still goes into that state, but nothing happens. See, the memory is in the no-op mode, register is in the no-op mode. It's just nothing happens. So cycle goes low, nothing happens. Now, next clock cycle, it is a write back. Okay, so what it is trying to do, whatever result of this addition, it should be stored back into the register 1. That's the instruction means. So basically it try to achieve that to the write back. Write back means write back to the register file. It's always write back to the register file. So remember, ALU sent a data 10 to the controller. It sends there, okay, that write data to be 10. And I need to write in register 1. So controller sends that 1 to the write address. And controller put the register file in a write mode. See, the read becomes 0, write is 1 at that point. And that's where it initiates the write operation into the register file. And another thing happens in the write back. Your program counter gets updated. So it's going to the next instruction to be fetched, which is from the address 4. Okay. Then clock goes low. Still in clock cycle 5, nothing important happens on this lower clock. It goes into next clock cycle 6. Now at this point, your register file is written with that 10 in that register number 1, and that's conclude this first instruction. And controller goes into the instruction fetch mode. That means it needs to read the instruction from the memory. Memory is put in the read mode. Address 4 is sent over to the memory. Register file kept in a no operation mode. Low cycle, nothing happens. Then go to the clock cycle 7. Controller moves into the instruction decode register fetch state. Memory returns that instruction code. Controller parse it. And now it knows that, hey, I want to read from register 0 and register 1. Okay. So let me stop at this point and let me see if you have any questions so far. on the execution of the first instruction.
Professor,
Yes.
I was actually wondering if these, I guess, slides are available anywhere.
Not really. You can always look at the slide itself, that won't make sense. Basically, go to the video recording and watch it if you need to. I would recommend that to watch the video instead of having a slide.
I just think the visual representation is really good. So it would be cool if I could take notes on it.
Yeah, but that's what, like, it is for the video purpose only. Like, it is, yeah. If you look at the real slides, it won't make sense to you.
Okay.
I can guarantee that. It's a static, right? There is no action coming up there.
Thank you.
All right.
Professor, yes. I had a question. So the register file has at 0 index 0 value by default as a constant. So, but regardless of whether that's there, why do we need to write the first statement as retrieve index 0 from register at 10 and then rewrite that to register? Can't we just write it as write 10 to register? Or if we have to do an addition, can't we just write it as write 0 plus 10 to the register file?
That's a good question. This is a limitation of this specific assembly language, and it all depends on what you can write in the assembly language. You are constrained by that. So once you actually study the actual assembly language for this system, MIPS-like system, you will see you have only handful of instruction with you. It is not that widely varied. So that is one reason that you are stuck with that. Secondly is that you are thinking more like, okay, hey, if I directly write 10 into the register, it will save me like all the 5 clock cycle, right, Rahul? That's what
I'm kind of thinking. Yeah, it will save some time in this clock cycle. It'll save a little time.
Right. You are right in the thinking. But point is that, remember, these are all hardware, right? Now, to achieve the dynamic behavior on the instruction, it will make hardware much more complicated, making the hardware slower, and that will actually eat up any performance gap.
I see.
So it tries to, if we go through this old example, you'll see it becomes a very uniform step of action from the processor, which is very similar. It is doing this and that keeps the your circuit simple. And if you keep your logic circuit simple, it can make processor faster. So if you do extra steps,
that makes sense.
It don't actually affect your final performance of the program.
That makes sense.
Okay, but I think many of these things will be cleared up in the 147. When you go and study that, you will actually build up a processor like this, and then you will see what I'm saying right here. So it will be like maybe another semester down the line. Okay, so but these are good questions. Keep those questions coming up.
I keep thinking I'm not understanding stuff properly right now because it's 6 a.m. over here. But yeah, I'll keep asking if I have anything.
Sure. Okay, now let's move to our next instruction, how this is achieved. Now here, your processor is definitely knows, after parsing this machine code, it need to access both the content of R1 and R0. So at the same phase, it sends those two addresses, 0 and 1, to the register file, make the register file in a read mode, and yeah, that's it. Now clock goes low, nothing happens. Next clock cycle, clock goes high, controller goes into exe phase, and here what it needs to do is really the content back from R0, you need to add 0 on top of that. Now what that content back from the register file sends 0 and 10 from that previous read instruction, and from that it picks up this 0, sends over the ALU, sends this 0 over the ALU and do addition, right? It's kind of, again, like as Rahul mentioning, this is so trivial, like why processor need to do it? Again, it's the hardware way of doing it, make it simplified steps. So it does it, and then next lower of clock cycle doesn't make many difference. Clock cycle 9, it goes into mem step. Now you see here's something we need to do with the memory, because we want to write into the memory with the content of R1. So what it will do, it takes the result out of the memory. So ALU at this point is actually computing the address of the memory to be accessed. So it is 0. This 0 is sent over in the address port of the controller towards the memory. Data 10, which came from the register file on the data 2 on the previous cycle, it sends over that data 10 to the memory, and the memory is made into the write mode. Read to 0, write to 1 in this cycle. And then it goes low, then clock cycle 10, your write operation is complete at that address 10, address 0, 10 is written, which accomplishes your high level instruction A equal to 0, right? So at this point, that is done, and state controller goes into the write back state, program counter update to 5, and that's it. Nothing else is interesting happening in the whole system. Now it carry on like this. It's the same thing, like next instruction is at the clock 11. It is the R1 equal to R0 plus 20. It is similar to the very first instruction. Similar thing will happen. Controller sends the read address, instruction address in this cycle. Then next cycle, at the start of the next cycle, memory sends back the machine code. It parses the data. It need to read from the R0s. So it requests the register file to read from the registered 0. And then next clock cycle, it will go to the EXE. In this point, it need to add 0 and 20 together. So it involves the ALU to do that. And then it goes into the mem cycle, where it is not a memory bound instruction. So nothing will happen in this mode except ALU returning that 20 result 20 at this point. And then on the write back side, it will write that 20 into the register 1, which in the next cycle, by next cycle, it will be completed. On the register 1 is 20, and next instruction fetch start happening. Your program counter already updated in the previous write back state. Now at this point, we are trying to start executing this instruction, which is pretty much similar to this instruction, the one we discussed. So let's quickly glance through. It fetched the instruction. Next cycle, it gets the instruction. There it knows I need to read from register 1 and register 0. That's what happens. And then go to the EXE. There it knows it need to calculate the memory address by adding up these two numbers, 0 and 1. It sends to the ALU. Then also data is coming back from the register file, 0 and 20. Then in the memory state, what happens? This address value that ALU calculates sends over to the address. Data value sends over to the data port. Memory is given into the write mode. And next cycle, it basically written back into that one. And at this end of this whole cycle, that means we are accomplishing this this instruction, b equal to 20, right? And then what happens? Write back, there is nothing to write back, so nothing happens in this state. And then clock cycle 21. Now it try to read from that memory 0 and bring it into the R2. So similar thing happens. Instruction fetch is fetching the next instruction from the memory. Then next clock cycle, your instruction machine code comes into the controller. There it knows, okay, it needs to read from the R0. So it sends out that reading request to the register file with both address to 0. And then on the exe stage, what you need to do is compute the address M0, R0 plus 0, which is 0 plus 0. It sends to the ALU. And while register file already sent back the data to it. And next cycle, in the memory cycle, what you need to do now, it need to read from that address. So it sends that data 0, address 0 to the memory, put it in the read mode, and then wait for that memory to return back. Now it is reading from the 0 address, so it will return the 10 onto the controller. And the write back stage, what you need to do, write that data into the memory, into the register file, address 2. So it's basically just doing that controller. It sends the write address to 2, pick up that data, send it to the register file, putting the register file into the write mode. So next cycle, you'll see that 10 is being written in register 2. It is a new instruction at the starting from address 8. So it is the same similar instruction like the previous one. It is R3 equal to read from the memory location and put it back in the register. So similar things will happen just like the previous instruction. The instruction came back, register file is read. At this point, memory address is computed. Then at the memory cycle, the address is sent over the memory to be read from it. Next cycle, 20 came back from the memory, and controller writes that 20 into the register 3. So it is sending those information to register file to write that back. And then by the next cycle, this 20 will be stored in the register 3. Next, instruction fetch is coming from the address 9, which is where we are doing this. So basically, it is access the register 2 and 3, add them up, put the result in register 4. So let's see how it does it. So it comes back with that instruction, controller parse it. It knows that it need to read from register 2 and 3. So it sends out that 2 read address into the register file with the read, putting it on the read mode. And the next cycle, register file sends back that 2 data, 10 and 20 over the line. And then also at this mode, it picks up these 2 operands, sends to the ALU 10 plus 10 and 20 with the addition operation because it's saying to add it. So next cycle, is ALU will return with the value 30. And since it is not a memory bound operation, nothing will happen in this cycle in terms of memory or register file. And then clock cycle 35, write back, pick that result 30 and store it in the register 4. So at the end of this cycle, beginning of the 36th cycle, your result is stored in R4. And now we are at the very last instruction of this program, which is telling that read from register 4 and also read from register 0, compute the memory address, whatever that address is, write back the content of the register 4. So we are fetching the instruction, parsing it. Here it knows it needs to access R4, R0. So those 2 addresses are set over the register file with putting it in a read mode. Next cycle, register file sends the 0 and 30 to the controller. Controller try to make the address calculation by sending this 0 over the ALU and this immediate 2 over the ALU and an addition operation request. And then at the memory cycle, ALU comes back with the result 2. So it put that address 2 for the memory. And remember, it also register file also returned the data 30 that sends over the memory with the write mode on. So it is read to 0, write to 1. And then at that end, starting of the cycle 40, memory stored that value 30 in address 2, which in essence, in the high level instructions equal to A plus B. That's what achieved at this end of this function, end of this state. Now it is still in the write back state. Nothing will happen because it's not a register bound instruction, and then it will go into the next instruction fetch with the instruction 11. We don't know what that instruction is. Let's not worry about that part so far. Question?
Yeah.
Yes.
So will the data in register file, like address 1, 2, 3, and 4, will it stay there
Yes.
until it's overwritten?
Yeah, it will overwritten for the next instruction.
Okay.
I have one too. What did IF stand for again? I forgot that one. IF.
Instruction fetch.
Oh yeah, that's the one. Thank you.
I had a question.
Yes.
Is there a particular reason why the memory address is written the way it is? The register 0 plus 0?
Yes, because this is the assembly provided function that is always with respect to a base register. We call this a base register, and memory is always address is calculated based on a base register. So some register value plus some immediate value. That's how we always calculate the memory address.
Is the 0 an arbitrary value then?
Not really. It is basically targeted value, like compiler assigned a value 0, right?
Mm-hmm.
The question is, how can I come up with that value at the address with the constraint that I need to calculate the 0 with some register content and some immediate value. Okay. So if it is, for example, if it is 2, right, address 2, compiler assigns some address 2. How can I come up with this address with reading of an register and an immediate value? So here the easiest way would be read the register 0, which contains 0, and add on top of 2 on top of that. Now, given that, that means, let's say my register 5 had content 2, for example. Let me see if I can annotate it. Let's say I have 2 here. Okay. Now, what I could have done in this, at this point here, what I could decide, instead of having a R0 plus 2, I could have R5 plus 0. Okay. But ultimately, I want to make sure I come up with the address of 2. Make sense?
Mm-hmm. Thank you.
Yeah, may not make sense like all the way 100% right now, but wait for till you come up with this assembly language study. I think 3-4 lecture down the line, then you'll start realizing this part. But keep your question in your mind, like why this is. Okay. All right. Now, okay, cycle 41, instruction fetch. I don't know. Now we have this question, right? These 3 high-level instructions is mapped to like almost like a 8 low basic level instruction. On an average, let's say 3 basic level instruction per one high level instruction. And it took 40 clock cycle, like as Rahul mentioned, isn't it like wastage of cycles and stuff like that? Can we save things and so on and so forth? Question is it too slow? With this question in mind, let's go for a break, 5-minute break, and we'll be back on 6:50 to discuss this part.
Anyone still have the headphones on?
Hey, what's up?
Hi.
Hi.
Is this your last class for the day?
Yeah.
Neat. Same here. How many classes have you had today? I had 2 other classes before this.
Fortunately, I
One
had all
math
my
and one
classes.
history.
I have all my classes today, and like one class on Mondays and Wednesdays.
Oh, you got a bit packed Tuesday?
It's a bit unbalanced.
Yeah, it's Tuesday over there.
Yeah.
Very unbalanced. But then hey, you get like 5 days of the week with no classes.
Yeah.
Does that help? Or does the one day of many classes make you regret having this one day?
It's a lot of classes ask to watch lectures or read material before I enter the class, so I don't really have much time anyways. It's
I see.
alright.
Are you majoring in computer science as well?
Yeah, I'm doing CS.
All right, let's get back into the business after the break. Uh, so we had this question, right? This why if is it too slow for the computation? Let's pitch in the idea of this clock speed, right? So you remember, like if you buy a laptop or desktop or anything, you first thing you look at the what processor and what is the speed of that processor. So can any one or two of you share what's your system speed is? Yes, no?
A lot. I forgot.
Okay, so you don't remember your spec
4
of your.
No.
gigahertz.
Now, since you are starting hardware, you need to go back and remember, or at least look at what the spec look like. Anyone else like remember? Yes, Andrea.
Gigahertz.
What's that?
4 gigahertz.
4 gigahertz.
Yeah.
Wow, that's a wonderful speed. Cool.
Yeah.
Okay, let's be on the conservative side. Okay, let's say this specific system is running on a 1 gigahertz speed. Okay, like 1/4 of the speed that Andrew is saying that his system is. That means your time period is really 1/1 gigahertz, which is basically, if you calculate, convert the unit, it becomes 1 nanosecond, which is 10 to the power minus 9 second. And remember this clock period, clock cycle we talked of? It is that it really means each basic instruction takes 5 clock cycles to be completed. Like this 5 cycle will be completed in 5 clock cycle, which means 8 basic instruction will take total about 8 into 5 with this clock time, like this period. It is 40 nanosecond. Or in other sense, if we want to calculate from here or calculate from these 5 nanosecond total time per basic instruction, in 1 second, we can actually compute 200 million instruction, right? Just do a mathematical computation there. It is 10 to the power 9 by 5 is 2 to the power 2 into 10 to the power 8, which is 200 million basically instructions. Basic instruction can be executed. And even if you think that the high level program you are writing, each high level statement breaks down into, let's say, 5 basic instruction in average all over the program. That's an average statistics. That's a 5 instruction per high level instruction. That means per second we are actually executing 200 by 5, which is like 40. Yeah, 40 million instruction, high level instruction, which is a huge, right? So even if we are seeing there are some sort of repetition of operations, some date cycle, like, okay, memory, if it is not a memory bound operation, nothing is happening. If it is not a register write operation, write backstage, nothing is happening. So there is a possibilities to optimize on that, even if we think it, but it's not worth, because we are already executing in a blazing speed. So that's the perspective I want to bring in to all of you, that even if like this whole explanation took almost like a 40-minute, that only this simple 3 high-level instruction, how they're accomplished in a processor. But remember, processor is executing things at a very, very high speed, and that's where the benefit is coming from for this any digital system. So what are the key takeaway from all this discussion? Before I go there, any question? Okay. So first of all, what we probably realize by now, computer is very simple state machine with a capability of very simple algorithmic step. If you are thinking so far, computer is an intelligent system, is an intelligent machine, it is not. It is probably the dumbest thing in the whole world. It basically does very simple, repetitive algorithmic step. Intelligence comes from the software program being executed at very astonishing pace. That's where the power lies of a modern computer. It can execute things at a very, very astonishing pace, but intelligence-wise, core intelligence-wise, this is not an intelligence system. It cannot come near to human intelligence. So far, people are trying their best to achieve that, but that's, I believe, more ways to go there to achieve a human intelligence, that what we call intelligence. Next, specific hardware is accessed at very specific state. For example, if you see the memory is accessed in the instruction fetch state and the mem state. Register file is accessed during the IDRF state and write back state, and ALU is accessed in the EXE state. And almost the next observation from that memory is accessed at least once per instruction and is accessed twice for the memory access instruction. So sometimes actually people mixed up that if it is not a memory bound instruction, that thing memory is not accessed at all. But remember, at the instruction fetch, is always need to access the memory to get the instruction from the memory, right? So memory is accessed at least once per instruction. Here by instruction, I mean the basic instruction, and access twice for the memory access instruction. Please keep that phenomena in mind. Next, EXE state calculates the memory address of the data memory to be accessed in the very next memory state. So mem state access the data memory. So down the line, you will see actually we conceptually separate the memory system in multiple parts and for the multiple different purposes. One part is assigned for stored the program execution code, the machine code. Another part is stored for the data. Another part is used as a dynamic memory allocation, like you do like a new operation in the Java program, malloc operation in the C program, that kind of thing. A part is pre-dedicated that, okay, this part will be used for the dynamic allocation. And there are many conventional usage of the memory as such. So we'll see that down the line. And next is program counter is updated at WB state. This always happens at the write back stage. Program counter is also updated. And last but not the least, keep the control signal to known logic value all the time. This may not be very significant at this class, but it will become very much significant in next, like CS47, that study. Okay, but nonetheless, keep that in mind. Keep the control signal to known logic value all the time, especially you don't want to write any unwanted thing either to the memory or to the register accidentally in this hardware system. So the default values for control values for those register file and the memory controller goes for is a no operation, is a 0, or at least it goes with a read operation. Read operation is a safe operation, a reading from the memories or the register file. Danger operation is always a write operation because it goes and change the state of the program. I know if you are unwantedly writing accidentally onto those memories and storage. So keep those things in mind, those points always, and then we will move to the next study, next successive study. Question so far? Okay, if we don't have a question, then let me see what are coming up for the next lecture. So by the way, any question on the number system study or anything? You can always put in the discussion board and we can pick up there as well. Okay. Let me share. Speak to, okay, here. All right, so we are should be at the end of the lecture 3 by this time, as the timeline says. So I hope you have all reviewed till this. And next we move on to the next part, programming a processor. Okay, this is very interesting. That is the bread and butter of this course till the midterm. So we are going to study how to program a processor. Okay, we have done it, definitely done it from the high level programming using Java or C or C++ or scripting like Python. We have done it. Now we are here to make a programming a processor at a low level, like without the help of high level interpreter or compiler like Java or GCC or Python interpreter. Without help of them, how we can actually directly program a processor, we'll learn here. So please visit the introductory module page, watch this video. It also gives you the module objective, etc., etc. And then the next lecture is on programming a computer. Let's see what is there. First of all, this one has about 6 videos, okay? Different videos and different convention, etc., etc. Let's see what we have on the lecture side. Okay, it has some reference to your textbook if you would like to have extra notes there. It is chapter A1, Computer Organization and Design by Patterson. So topics here we'll be seeing is the programming, conception of programming, programming languages, and some study of the assembly code. Let's see what are there. On the programming side, it tries to explain that what the program is really, like by conception, what is a program. And then we go forward from there. This is pretty much theoretical discussion from that standpoint, and it basically wants to build up your basic conception about a program. Okay, many of you have probably a different conception about programs, so let's be on the same page what we mean by a program in this class and in throughout really what it means. And then we go with the topic of programming language. Now this topic is basically talks about what are the different languages that computer understand. We'll see it basically understands 0 and 1. It doesn't understand anything else. Whether it is Java, C++, Python, computer does not know it. Simply, a computer as a system only knows 0 and 1, that language. That is the only very language it understands. Okay, so let's build our concept on that, and then how we'll see what is the relation between that language based on 0, 1, and from there, how it kind of goes into the machine language, how it maps to the assembly language, and how it goes into the high-level language, and what is the relation between them, how they're transformed from one to another. So there, these computer tools comes up in place, like a compiler, assembler, where we as a human talk in a high-level language that we are comfortable with, and this tool convert that same program, same concept into a machine code, which computer understand and can execute. So this is the basic idea that we want to have and build up at the end of this study. And then we'll move on to look at the detail about the assembly code. What is the assembly code, how it looks like, and so on and so forth. So we basically had some basic discussion over there. What are the different parts of the assembly codes? Then we go and study the MIPS, that specific processor called MIPS assembly code. what are the different types, and what are the types format, how we can give an assembly instruction, how we can convert into corresponding machine code. That theoretical discussion happens here. So we have example of R-type instruction conversion, I-type instruction conversion, and J-type instruction conversion. Please go through that. And then we go with the role of the assembly code in the whole system, and also we'll discuss some of the pros and cons of the assembly level coding. So saying that most important part is to ability to convert thing and have a clear conception of these formats, okay, machine code formats, and how from a mnemonics sample assembly statement, how we can convert it into a machine code. That is very much important concept for you to understand. Also, other thing you need to put emphasis on is how these number of bits given per field, like let's say someone, it is not arbitrary, that I can say. Immediate is given 16 bit, RT is given 5 bit, RS is given 5 bit. This bit allocation in the machine code is not arbitrary. There are some reason behind it. Please try to find that out, why it is, like through analytical discussion and through some of this text, some of the videos that I try to explain, most probably I have explained there. Please try to find out why are these number of bits are assigned. And if I give you with a different machine configuration, how these fields get changed, number of bits get changed, that would be very interesting things to observe and understand. Question? All right, then we can stop tonight and see you all on Thursday.